Good morning. This is L. Shivayamini from Annamacharya University. I'm working as an assistant professor in the Department of ECE. Today, I'm going to discuss about architecture of embedded system. In the architecture of embedded system, first I want to discuss about the hardware architecture of embedded systems. The hardware architecture of embedded system consists of many blocks, which is having CPU, main one, memory, clock circuitry, watchdog timer, reset circuit, chip select, input-output devices, sensors, transducers, ADCs, and DACs. It is nothing but analog to digital converters, digital to analog converters, keypad, LEDs, LCD, communication interface, debug port, as well as power supply unit, which is shown in the above figure. So now we can see the figure. We can observe all the blocks present in the hardware architecture of the embedded system. Now coming to the first block, CPU. That is nothing but the central processing unit. In this, we are going to discuss about the processor. So in this processor, we are going to discuss about the internal architecture of a processor, which consists of registers, that is A register as well as B register, which are known as the math registers. So A registers can be used for addition and subtraction, and B register is used for multiplication as well as division. Then it is given to the ALU, arithmetic logical unit. Then we are having the stack pointer, memory address register. So for this memory address register, we are having the address bus. Similarly, instruction pointer, memory data register. This memory data register is indicated by the data bus, as well as the instruction decoder. So this all comes under the control unit, and it is controlled by the controller status bus. This is the internal architecture of the processor. Next, coming to the architectures. So architectures are classified here in two types. One is the von Neumann architecture, another one is the Harvard architecture. The difference between these two architecture is mainly the memory unit. In von Neumann architecture, we can see the memory unit is same, whereas for program memory as well as the data memory. Whereas in Harvard architecture, we can see the difference. Here, the program memory is separated as well as the data memory is separated. Comparison with the von Neumann architecture. So this is the main difference between the von Neumann architecture as well as the Harvard architecture. That is nothing but the memory unit. In von Neumann architecture, the memory in von Neumann architecture, the memory unit is same for program memory as well as data memory. Whereas in Harvard architecture, we can see the difference between the memory unit. That is, program memory is separated as well as the data memory is separated. Program memory is given to the program memory address bus to the CPU, as well as data memory is given to the CPU by data memory address bus. Next, coming to the interrupt. Interrupt is nothing but a signal to the processor. Whenever the event has occurred, automatically the interrupt is generated. Each interrupt will have its corresponding interrupt service routine. When there are more than one or two interrupts, automatically the priority is given so that the processor executes the highest priority interrupts. So coming to the processor classification, here the processors is classified into two types. One is the complex instruction set, another one is the reduced instruction set. So the main aim of complex instruction set computer is nothing but by increasing the complexity of processor architecture, whereas in RISC, it gives more importance to the software. So it has small number of registers are available, whereas in this, we can observe there are large number of registers are required. So in CIS, we are having the large number of instructions, whereas in RISC, we are having the complex instructions are available. As it has complex instruction, it takes several cycles to execute. It has simple instruction, it takes only one cycle to execute the instruction. So in order to evaluate the processor, we have to consider some specifications to evaluate the processor. One is nothing but the clock speed, length of the register, width of the data bus, address bus, number of registers are used, internal RAM, internal ROM, peripherals like timer, UART, ADC, DAC, something, interrupt lines, as well as the programmable input-output lines. By using these specifications, we are going to evaluate the processor. Next, coming to the another block, that is the memory unit. Here the memory is classified into two types. One is the program memory, another one is the data memory. The main difference between program memory and data memory is the contents in the program memory stores the firmware permanently, whereas the data memory contains the erased whenever the power is off. In microcontroller, we observe both program memory and data memory are on chip. If the capacity of the internal memory is not sufficient, then we are going to take the external memory. Therefore, the memory chips are classified into RAM, ROM, as well as a hybrid memory. Again, RAM is classified into two types. One is the static RAM, another one is the dynamic RAM. The difference between static RAM and dynamic RAM is nothing but in static RAM, the contents loses whenever the moment the power is switched off. Whereas in DRAM, the contents are remained even for a fraction of second. That is the main difference between the SRAM as well as the DRAM. So coming to the SRAM is very faster and consumes the less power, whereas DRAM is very cheap and hence it is used when high capacity RAM is used but at low cost. ROM. So in the previous slide, we discussed about the RAM. Now we are going to discuss about the ROM. So ROM is nothing but in this already we discussed that the contents are not erased whenever the power is switched off. The contents remain. So here the ROMs are classified into different types. One is the programmable ROM. Another one is the erasable programmable ROM. Third one is the electrically erasable programmable ROM, non-volatile RAM, as well as the flash memory. These are the different types which are we used in the ROM. So here the memory unit is maintained. How the processor is connected to the memory unit can be explained in this figure. The processor is directly given to the memory unit by address bus as well as the data bus. In this figure, we observe the RAM, ROM, as well as the flash memory. Next, clock circuit. In order to execute the instructions, we specifically needed the clock circuit. To generate the clock signal, we required the crystal as well as the crystal oscillator is required. For some processor, this oscillatory circuit is inbuilt. Otherwise, we are going to take the external crystal oscillator. So watchdog timer as well as the reset circuit. If there is a need to reset the processor, the reset may be done by using the watchdog timer. That is, here the timer is set to a very large value and it is decremented slowly. If the timer value is reset to 0, the processor is reset to a reset signal. In this way, we are going to done the reset in the circuit. So another one is the sensors and transducers. As you already know that in order to convert the real-time information into the electrical signals, so this can be achieved by using the sensors and transducers. In this, we are going to discuss about some important sensors like temperature sensor in order to measure the temperature, light sensor, accelerometer, pressure sensor, microphone, speakers, video cameras, as well as the monitors. Next, ADC and DAC. As we all know about in communication, in order to convert the analog into digital, digital into analog, we are going to use the analog to digital converter as well as the digital to analog converter. These can be achieved by using the sampling as well as the quantization. In sampling, the amplitude levels are measured at regular intervals. In quantization, the sample values is converted into a number. So in this way, the process of ADC is done by using the sampling as well as the quantization. In sampling, first the samples are going to be sampled, then it is quantized. That is can be done to a nearest integer value. Then the data is encoded. This process is done by using the ADC converter. Next, keypad. Based on the application, an embedded system has to be provided with a function keypad to input data as well as the commands. So the figure shows the keypad. For example, for pass, first forward, go to first file, go to last file, etc. Next, LEDs. LEDs are mostly used as the output devices in the embedded system. Red, green, and yellow LEDs are used for the status display as well as indication of visual alarms, events like power failure. Next, LCD. In order to display any messages, we can use the LCD, liquid crystal display. So SPI, serial peripheral interface, which is developed by the Motorola. In serial peripheral interfaces, we are having one is the processor unit and another is the peripheral unit. This can be achieved by using four types of signal. One is the master or slave in, master in slave out, serial clock, as well as the chip select. By using these signals, we are going to achieve the peripheral interfacing. This is the I2C, inter-integrated circuit. So in order to inter-integrate the circuit buses, we are going to use the ITC line by using the serial clock as well as the serial data. By using these lines, we are going to connect different devices. Debug code. Debugging the processor baseboard is very difficult. In order to achieve this mechanism, we are using to take the JTAG. So here the JTAG code consists of four signals, that is test data input, test data output, test mode select, as well as the test clock. By using this, we are going to debugging the code. So these are the some communication interfaces we are going to use in order to convert the hardware architecture to software architecture, like serial interface using RS-232, RS-422, 485, USB, infrared, Ethernet, IEEE 802.11, Bluetooth radio interfaces. So in order to achieve this, the main power supply unit is used. So which consists of DC voltage like 12 volts, minus 12 volts, 5 volts, minus 5 volts, plus 3.2 volts. So this power must be required in order to work the hardware architecture of the embedded system.